Hello, my name is Jeff Hittinger. I am the director of the Center for Applied Scientific Computing at Lawrence Livermore National Laboratory. But more importantly, for the proceedings today, I am a proud alumnus of the DOE CSGF program and the chair of the Frederick Howes Scholar Award Committee. Dr. Howes managed the DOE's Applied Mathematical Sciences program during the 1990s and was a strong supporter of the DOE Computational Science Graduate Fellowship. The Frederick A. Howes Scholar in Computational Science Award was founded to honor his memory and service to the computational science community. One or two Howes Scholars are named each year from the recent graduates of the program based on their outstanding leadership, character, and technical achievement. This year, we honor 3 recipients, one 2020 awardee and 2 for 2021. The selection committee is pleased to name Dr. Gerald Jerry Wang the 2020 Frederick A. Howes Scholar in Computational Science. Dr. Wang received his PhD in mechanical engineering from the Massachusetts Institute of Technology in 2019 and is currently an assistant professor of civil and environmental engineering at Carnegie Mellon University, where he directs the mechanics of materials via molecular and multiscale methods laboratory. Jerry was selected for his demonstrated leadership, character, and outstanding technical achievements in computational science. Jerry's doctoral research focused on understanding the nanoscale structure of fluid flows in confinement and the associated transport properties within those flows. Since the time of the first molecular dynamics simulations of confined fluids in the 1970s, it has been known that at these small scales, the fluid close to the fluid-solid interface forms a layered structure. Using careful molecular dynamics simulations, molecular mechanics arguments, and asymptotic analysis, Jerry derived explanations for this type of flow and published the first paper theoretically characterizing this layering effect. Building on this work, Jerry developed models and engineering design principles to describe the effect of this layering on transport under nanoconfinement, as well as the well-known but difficult to model phenomenon of slip. From this work, Jerry published a novel model for quantifying slip at a fluid-solid interface from first principles at the atomistic layer. As a postdoctoral associate in the Department of Chemical Engineering at MIT, Jerry used computation as a way to bridge between scales, to study suspensions of attractive colloidal particles, and to understand how friction between neighboring particles affected their transport properties. Jerry's fundamental contributions to understanding the behavior of nanoconfined fluids could have far-reaching impact in the application of nanomaterials to filtration and desalinization, carbon sequestration, drug discovery, and chemical sensing. Jerry also has distinguished himself as a leader of great character. He's well regarded for his effusive, kind, and positive personality, and his skills as a team player and team builder. Jerry was actively engaged in the Student Advisory Board for the Edgerton House, a graduate student residence at MIT. For 2 years, he served as president of the student government, organizing over 100 community events, and he was relied upon as a mature, caring individual of the highest integrity to help address topics as mundane as IT infrastructure to serious personal tragedies. He tirelessly served the students in the House and built around him a leadership culture and cohort of student leaders that survives to this day. With a passion for teaching and mentoring young scientists and engineers, he was appreciated at MIT not only for the depth of his knowledge, enthusiasm, and excellent communication skills, but also for the dedication and preparation he put into his instruction. Jerry also organized a campus-wide activity called Stick With Me, in which Post-it notes with words of kindness and encouragement were distributed and posted all over campus to show support for colleagues and friends. Through the Mind, Hand, Heart Innovation Fund, Jerry was able to grow this program of encouragement internationally. In 2017, MIT's Graduate Student Council honored Jerry with the Edward L. Horton Fellowship Award, presented to any student or group that fosters fellowship within the graduate student community. Gerald Wang is a computational scientist who not only excels technically, but also serves as a role model for others, both as a researcher and a human being. He embodies the qualities Fred Howes promoted in all early career scientists. Because of the challenges presented by reworking the annual program review into a virtual format last year, Dr. Wang was unable to give his House Scholar presentation. We therefore are very pleased to be able to give Jerry this opportunity now.
Hi, good morning, folks. It's really an honor to get the chance to be with all of you this morning and to share a little bit about some of the problems I've been thinking about over the last couple of years. To those friends, old and new, welcome, and it's great to be with you on this first day of program review. Even despite the circumstances, it's always great to have this chance to be together. Now, the title of the talk today is P.S. I Love You, because there are a whole bunch of PSs that we're going to talk about that have really shaped my experience as a computational science and engineering kind of person, and that have shaped my experience as a CSGF fellow, and that have shaped the research that I've done. The PSs that we'll be talking about are centered around the production of science for primarily soft matter, using particle simulations, plus some statistics, plus some supercomputing, all the way from the picoscale, or at least the very small scale, up to the pedestrian scale. Now, to kick off our conversation, the animating principle behind all of the work that I'll be talking about today, all of these particle-based simulations, is a classical principle, Newton's second law, F equals ma. But simply, the idea that drives all of these simulations is that as long as you tell me the forces acting between particles, I can, by means of numerical integration, figure out, deduce what those particles' velocities and positions over time are. And that's the essence of Newton's second law. What's left open in this prescription is where you might get those forces from in order to get this ball rolling. So we're going to talk in a moment about where one might turn to get those forces and in turn drive all of the school science and engineering. Now, the way that we're going to organize this very short little talk is we're going to first begin with a description, an overview of what kinds of forces show up in particle-based simulations. It's a talk that I certainly had absolutely, when I was entering into the program, even though particle-based simulations were what I was doing, I had none of this big picture perspective on how all of these ideas fit together. So this is really the little primer on particle-based simulations that I kind of wish I'd gotten as I was first starting off my PhD. So here we go. I'm a huge fan of the webcomic Saturday Morning Breakfast serial, SMBC, and I was very lucky in grad school to have the chance, in addition to doing a lot of fun research, to at one point meet the artist behind this, Zach Wienersmith. And over the course of our correspondence, he was even so nice as to draw a picture of me in the style of an SMBC character. So here I am, and at the chalkboard, I'm going to lay out some of the forces that show up in particle-based simulations. So these include, first and foremost, of primary interest in a lot of the work that I do, central forces. So these forces act along the line that connects the centers of two particles. And these can get either weaker or stronger as separation increases. Typically, at very, very small separation distances, these forces are pointing, directing the particles to get away from each other. And then as the particles get further and further away from each other, they start pointing inward. There's a weak attractive force pulling them in. So these are what we call central forces. There are also contact forces that can act between particles in general in any particle-based simulation. So these can push in all kinds of directions. The key defining feature of contact forces is that they're only in play if the particles are touching. And if they're not, then we don't have any contact forces. A third flavor of force that can show up in a particle-based simulation is a continuum-mediated force. So for continuum-mediated forces, the particles don't directly interact with each other, but rather they interact in the background with some continuous medium, which then acts on other particles. These forces tend to get weaker as the separation distance between particles increases. These show up widely across the field of suspension hydrodynamics, but I think that one of the best examples, one of the clearest ways to convey this idea is a video that has absolutely nothing to do with fluid mechanics. It is, in fact, one of my favorite videos on the entirety of the internet, and it's the following one. So here we see two goats or particles that interact via a continuous background medium. In particular, one goat jumps, it influences this continuous medium, the surface of the trampoline, and then that force propagates on to affect the dynamics of the other particle. So this is a great example of a continuum mediated force. Now, these forces show up for simulations that can operate at every length scale. At the smallest length scale that we'll talk about today, they can act between atoms and molecules, these forces, moving up slightly to larger molecules, macromolecules, colloids, polymers. You can also carry out particle-based simulations, and that's something that I've really enjoyed getting to do over the last couple of years. You can also move further up yet to the scale of billiard balls, or in general, things that are on the order of centimeters, or perhaps tenths of a centimeter or tens of centimeters, so larger objects. And then moving up further yet to the meter or tens of meters scale, you can also use particle-based simulations to study the behavior of pedestrians. That's another material with its own unique properties and its own unique behaviors that we'll get the chance to dive into in a moment. To connect these systems to the forces that we talked about earlier, I want to talk briefly about what kinds of forces show up in these different systems. And this is really the overarching picture that I really wish I'd had coming into this business. So when you're studying systems of atoms and molecules, these forces tend to be central, and their origins include quantum mechanics and electricity and magnetism. For those of you who are doing molecular simulations of various kinds, you are probably familiar with a large number of interatomic potentials who all derive their origins from quantum and E&M. Moving up slightly in scale to colloids and polymers, the forces that tend to come into these systems are central and continuum mediated. They're very often mediated by some fluid that all of these molecules, these large molecules, are suspended within. And the origins of these forces can include E&M, but also you can have significant thermodynamic driving forces and also fluid mechanical forces or hydrodynamics. As you move up larger yet to the scale of billiard balls or grains of sand, the primary forces in play are contact forces, and these bring with them ideas from the fields of elasticity and friction. Finally, as you go to the scale of pedestrians, the forces become contact forces and central forces. We'll talk more about this later on in one of the vignettes within this talk. And critically, because pedestrians are a form of active matter, you also have significant internally supplied forces. The origins of these forces include, in the case of contact forces, when two pedestrians are rubbing shoulders with each other, friction, but there can also be psychological forces at play. And in the case of internally supplied forces, those forces that cause a particle that is initially at rest to begin spontaneously moving, it's forces of that originate from biochemical processes in our body, breaking down things like cake and whatever else we happen to eat into motion that seemingly seems to appear when we look at the scale of a person, seemingly appears spontaneously. We saw a person at rest, and then we suddenly saw them moving. So this is the zoo of forces that run throughout pretty much all particle-based simulations and how they connect to specific systems that one might be interested in simulating. We turn now to the next PS that I want to talk about, and this is really where we're going to dive into some of the science that I've really had a great time getting to do, in large part because of the CSGF and the support of the CSGF. So this PS is something old, something new, something borrowed, something blue. This is very often given as advice for a successful wedding. In the case of the stories that I'm about to tell, I also think that the old, the new, the borrowed, and the blue is a pretty good recipe for producing great computational science and engineering. And we'll talk about each of these in turn. So here we go. Here's the first vignette. This one comes from the world of nanoscale fluid mechanics. And here's the idea. At the nanoscale, unlike at the macroscale, fluid slip is a huge deal. Fluid mechanics tells us that flow through a pipe is governed by the Hagen-Poiseuille relation. In particular, the flow rate scales as the pipe radius to the fourth power. That's in the absence of any slip or with a no slip boundary condition. But in the presence of slip, the flow velocity scales as the cube of the radius times the slip length, which means that if the ratio of the slip length to the radius is approaching unity or perhaps greater than unity, you start to have some exciting and non-negligible slip phenomena that show up in the system. This idea, by the way, is a unifying theme throughout the work that I do. Anytime you get an internal length scale approaching the magnitude of a confining length scale to the system, I think there's a lot of cool physics to be probed, and that's really what a lot of my work focuses on. So for this work, we're looking at this limit where L-slip over R starts to approach 1. Now, what's really exciting about this field of slip and in very, very small confining geometries is that a lot of people have been studying this over the last 2 decades or so and found a lot of really cool phenomena. For example, fast flow of various fluids through materials, through environments like carbon nanotubes. And in order to make sense of these kinds of results, we really need good, theoretically grounded and computationally and hopefully also experimentally validated results, data on these phenomena. To give a sense for how big this phenomenon is, I'm showing here a plot of the enhancement over the classical result as predicted by the Hagen-Poiseuille relation as a function of the size of the system. And what you can see is that these enhancements can sometimes be 1, 2, or even 3 orders of magnitude above the classical predictions. So there's really a lot of exciting transport physics that's happening in these systems. And there's applications for these ideas all across a range of quote unquote blue applications. So there's that something blue when we're talking about clean water, desalination, in general chemical separations, or flows through nanoporous media. It's really important to be able to understand the magnitude of slip at fluid solid interfaces. Now, business as usual in this field is the Navier slip condition. These ideas were laid out by Claude Navier in the early 19th century. So this is something old in this business. I think it's really important to study ideas from their theoretical and philosophical foundations going as far back as you can trace them. Well, in this particular business, the Navier slip condition, this is as fundamental as you can get in this business. So here's the idea. The Navier slip condition says that the slip velocity is linear in the velocity gradient at the boundary. What I'm showing on the right is a velocity profile without slip. That's the black dashed line. And in the presence of slip, the fluid velocity profile doesn't quite match up at the 2 boundaries, at the top boundary and the bottom boundary. The slip length is defined as the distance into the solid boundary that you would have to extrapolate the velocity profile in order to recover the boundary velocity. The Navier slip condition, which you can see in the lower right-hand corner, that's this linear relationship between the slip velocity and the slip length, has been shown rigorously to be the correct slip condition for dilute fluids, which leaves the open question, in dense fluids, in liquids, what's the appropriate slip condition to use? There have been a number of computational studies and also a handful of experimental studies over the last 15 years or so that have shown that the Navier slip condition fails, and in some cases fails catastrophically for liquids, especially as you go to higher and higher shear rates. So as you move these 2 plates at a great delta in speed between the 2, you can get really tremendous failures of the Navier slip condition. In order to tackle this problem over the past couple of years, something that I've been very excited to work on is to develop a theory for hydrodynamic slip that fits within the broad theoretical framework of molecular kinetic theory. I think this is a hop, skip, and a jump in the right direction. Here's the idea. In brief, when you look at a solid interface, like for example, at the surface of a sample of graphene, if you zoom all the way in, you're going to see a regularly repeating pattern if it's a pristine surface. And so if you have any fluid at that interface, it's going to experience this regular corrugated potential. The whole idea behind this molecular kinetic theory approach to slip says that slip comes from fluid particles absorbed within this corrugated energy landscape, carrying out little thermally activated hops, sometimes in the direction aligned with fluid flow, with the background fluid flow, sometimes oriented against that direction. The background fluid flow serves as a kind of biasing force or a kind of peer pressure to go one way versus the other. And the picture that I'm trying to lay out here is that slip comes from hopping in the direction aligned with that flow a little more often than the other direction. If you work out the kinetic theory calculations, you can develop an expression for what the slip velocity is as a function of a characteristic length and time scale for jumps, the fluid-solid interaction energy, the total amount of fluid absorbed at that interface, the viscosity of the fluid, and critically, the shear rate. What's super exciting about this expression is that if you consider this in the limit of fairly low shear rates, or in general, low values of that argument for the hyperbolic sign, you can recover the Navier slip condition, this linear relationship between the slip velocity and the shear rate. And you can also get an explicit prediction for what the slip length is in terms of microscopic parameters. This is a really exciting development that earlier models for slip are not necessarily able to do quite as well. So it's a theory, it's a conceptual framework that I think is super exciting. It's built upon a lot of ideas that are a little bit older and in some cases borrowed, which I think is one of the, to come back to that theme, one of the great things that CSGF enables you to do. It really gives you the freedom to spend time reading older literature and really getting a firm foundation, a firm grounding in the ideas that you're working in. It's something that I really enjoyed over the course of my time in CSGF. And I think it also was very directly responsible for being able to do this kind of work. The something old and something borrowed here, in particular, traces back to work by Blake and Haynes in the late 60s. Their work in contact line dynamics really created the foundation for molecular kinetic theory that's leveraged very heavily in developing this model. What's been a lot of fun to do with this model is to run a very large number of simulations and to compare the results of those simulations against the predictions made by this model. So this model makes very nice predictions for example, how the slip velocity varies with the shear rate. It makes many other concrete predictions that you can test. And by running quite a few simulations, taking advantage of the high performance computing chops that CSGF imbues in all of us, we've really been able to see some nice verification of the predictions made by this model. And in fact, there's also nice agreement between this model and some results that you can see in experiments, in particular experiments that probe slip velocity as a function of the shear rate. You can see this clear nonlinear behavior indicating that this is indeed not just business as usual Navier slip condition. All right, so that's the nanoscale fluid mechanics story. I want to turn now several orders of magnitude, about 10 orders of magnitude larger in length, to talk about another very, very interesting kind of particle-based simulation that you can do. This is something that I've been really getting into over the last year and have had a lot of fun doing and learning about, and that's pedestrian dynamics. So really quickly to set the stage, knowing that we have a lot of molecular simulation and computational chemistry people in the room, the kinds of techniques talked about in the previous section may be familiar to a lot of you. The core animating principle behind pedestrian dynamics may be a little bit less familiar. So we'll go over this in brief. Same pictures before, we just need to get those forces somehow, and with those forces in hand, we can play out Newton's second law to get particle trajectories. In the case of pedestrians, the forces are a combination of selfish forces, I'll term them thusly here, that impel us to always try to get to the target velocity that we want to as a single pedestrian within a flow, that push us to get to that speed. And if we're slower than that speed, we try to walk a little bit faster. There's a little random forcing that we have to put into these simulations to reduce stalling events. These are basically those events that occur when you're in a grocery store aisle or a narrow sidewalk and you come head to head with somebody and you kind of have that awkward song and dance where you're trying to get out of each other's way. So we need to put a little random force in there to avoid those. And then we also have, at the heart of this story, the social interaction term. That's the gradient of a social interaction energy, which we can split into a far field component and a near field component. Now, within this decomposition, the near field component accounts for what one might term the brushing shoulders term. So this is in cases where two pedestrians are near contact or they're at contact. This is the dissipative interaction they experience by literally brushing against each other. The far field term, which is the subject of the vignette that I want to tell now, we might think of as a collision avoidance term. So this term encodes how pedestrians try to avoid each other, and they try to avoid each other starting at a certain distance d naught, which characterizes the personal space that each one is trying to maintain. So this energy doesn't take appreciable values until the separation distance d is on the order of d naught. All right, so this is how pedestrian dynamic simulations work. By the way, if you want to read more about these kinds of what are broadly termed social force models, there's a couple of neat references there. So here's the question that we seek to answer. Over the past year, as we've put over the past more than a year, as we've gotten used to the new normal, the new circumstances of the pandemic that we live in, we've increasingly started to see situations like this. These are shoppers in Peru lined up to go to the grocery store, exhibiting absolutely remarkable order and a lot of separation space between people. We see this not only in shoppers, we see this in classrooms, we really see this in every facet of our lives. Even as the pandemic has ever so slightly begun to recede, we're still very, very conscientious about the amount of personal space that we're maintaining, especially when we're around strangers, especially when we are around folks that we don't know, and we don't know about their vaccination status, and we don't know about their health. So everybody amongst us, we're all very conscientious about that personal space. The question that I want to ask in this work is, how has the need for increased social distancing, how's that affected the dynamics of pedestrian flows in confined environments? To bring back that theme from earlier, what's really going on here is we're studying a particular dynamical system in the limit that the personal space that individuals want is now much closer to the characteristic length scale of the confining environment, of the walkway that they're in, as compared to before. If before we wanted 2 or 3 feet and now we want 6 feet, well, that's a whole lot closer to that confining length scale, which for a typical hallway might be 5 or 6 or 10 feet. It's a lot closer to that than it was before. And again, as this ratio approaches unity, you can start to have interesting transport physics enter the question, enter the picture. So the kinds of simulations that we're carrying out look like the following. This is a pedestrian counterflow in a hallway showing 2 populations, one walking to the left, one walking to the right, and all these pedestrians interacting with each other according to those forces that we laid out earlier. Here's some of the takeaways, and there's really a lot that you can talk about. I'll highlight a couple. First off is that the more people you have, the more problems you have. And by problems, what I mean is the more jamming and slowdowns you have. So what I'm showing here is that at very low pedestrian densities, everybody's able to maintain that desired velocity that they're targeting. But as you pack more and more people in, as there are more instances of people running into each other and having to squeeze past each other, you're going to see lower and lower velocity until you reach a scaled density of order unity, at which point you start to enter the regime of jamming, and you really see these velocities fall to 0 very quickly. Now, this may not come as a huge surprise. We know that this is the case, but what's cool is that in these simulations, we can quantify the onset of jamming, and we understand when we're starting to get close to this and the magnitude by which the average velocity drops. When you add social distancing into this picture, it gets more stark yet. What I'm showing here, moving from the lightest lines to the darkest lines, are typical amounts of social distancing corresponding to pre-pandemic normal values. This 0.1 here leads to social distancing that's on the order of 3 feet or so. The 0.2 values, the darkest lines, are social distancing values that are length scales that are on the order of 6 feet. And what you can see here is that regardless of the hallway width, as you increase the preference for social distancing, you dramatically decrease the density at which you start to undergo this jamming transition. These kinds of results, again, although they're quite intuitive, they're also very useful for being able to do planning for all kinds of things. For example, even as the pandemic recedes, being able to think about smart and data-driven / physics-driven ways to think about returning to work, returning to campus, returning to the occupational spaces. We really want to know when people have more conscientiousness about distance, what's that going to do to flows? And we can quantify those kinds of phenomena using these pedestrian dynamic simulations. So that's something that I've really found to be a lot of fun to learn about, and it's been a very neat change from the work that I was doing before in more atomic and molecular scale physics, but it's grounded in the same fundamental ideas, and that's what doing great computational science is all about, is leaning into that transferability of ideas. We turn now to the next PS. The next PS is PS, a picture is worth 1,000 words. This is something that I had a deep appreciation for before, and I developed an even better appreciation as a member of CSGF. I learned an awful lot about visualization and smart visualization techniques from my peers from the CSGF community. That's one of the absolute best things about the program, is getting to learn from your peers in the program. So here are a couple pictures that show the computational science and engineering adventures that I'm getting to go on nowadays, and that I consider myself awfully lucky to get to go on. So at CMU, my group is called the M5 Lab. It's the Laboratory for Mechanics of Materials via Molecular and Multiscale Methods. Say that 5 times fast. I've tried. And we study all kinds of problems in that, making use of particle-based simulations for studying transport phenomena at a wide range of length scales, all the way from the nanoscale up to, we study heat transfer phenomena. That's one particular kind of transport phenomenon that we're quite interested in. We make a lot of use of high performance computing in order to carry out these simulations. We think about molecular scale design principles for sustainability. This is one blue or green, depending on which color you associate with this set of topics that we've really gotten quite into over the last year. And then going from those very small scales up to that large scale that I was just talking about, we also think about the physics of livable and equitable urban systems, including pedestrian dynamics. And these images, which are hopefully worth in the vicinity of 5,000 words or so, really show the large number of problems that you can tackle with a solid grounding in particle-based simulations. So we're coming now down the home stretch. The last PS that I want to leave with all of you is PS, one good turn deserves another. I'll say, especially for those first years on the call, that when I can still remember with great clarity that day when Lindsay Iltz called me, and I actually missed the call because I was in class, and I couldn't believe it when I got out of class, this missed call telling me that against all odds that I held in my own head, that I was going to get to join this program. I was absolutely ecstatic. I felt lucky as a duck, and I really couldn't believe it. And I feel like I've just benefited a tremendous amount from the support of the CSGF, from the Krell Institute and the community. And that one good turn really deserves another. You've all now gotten this chance to participate in this amazing program. And I hope that you all take this opportunity to pay it forward in your lab, in your department, in your college, and also in your community more broadly. And there's a lot of opportunities to do so. If any of you are curious about, outlets that one might pursue, even potentially counterintuitive outlets to pursue community betterment, please let me know, and I'd always be very happy to chat about that. But it's important to emphasize that one good turn, it deserves another. So with these 3 PSs and a whole lot more PSs under our belt, I'd like to thank you all very much for tuning in today and for being a part of this conversation. I'd be very happy to take any questions. And like I said, one good turn deserves another. I'm so unbelievably thankful to all the people who have helped make this happen. And I'm very excited to keep on having computational science and engineering adventures and to keep paying those good deeds forward. So with that, thank you all very much, and I'll be happy to take any questions.